Swayam Prabha. Digital India. Educated India.
Good morning and welcome to this next lecture on vibrations of plates and shells. Last time we completed the derivation of the partial differential equation and we moved on to the boundary conditions. So we were at this point. The boundary conditions look as follows: integral over time, integral over alpha 1 q to 3 star minus q to 3 delta u3. This is the externally applied shear force and this is the internal, plus m to 2 star minus m to 2 delta beta 2 plus m to 1 star minus m to 1 delta beta 1 d alpha 1 dt, and this is at alpha 2 constant edge. Then we have plus integral T1 to T2 integral alpha 2 Q13 star minus Q13 delta U3 plus M11 star minus M11 delta beta 1 plus M12 star minus M12 delta beta 2 d alpha 2 dt, and this is at alpha 1 constant edge. Now we have three boundary conditions at each edge, okay? Three boundary conditions at each edge, and we can see from here that the plate equation is fourth order in space, fourth order in x, fourth order in y, okay? So therefore at each constant edge you will expect two conditions. Two conditions on one edge, two conditions on the other edge. Similarly, two conditions on one edge, two conditions on the other edge, okay? But here we see that we are getting three conditions instead of two. We have three conditions on each edge, okay? So there is something to be done over here, and this was, as I said, observed by Kirchhoff and addressed. So what now he did is he looked at this plate this is my x or alpha 1, this is my y or alpha 2, and this is the z or alpha 3 direction, okay? So this edge, if I show this edge looks like this, okay? So there is a Q13 resultant, there is an M11 moment resultant, and there is a M12 shear moment resultant. Okay, that is this at an alpha 1 constant edge. Alpha 1 is a constant here, alpha 1 star at that edge. Okay, and if we look at it end on, if we look at it straight, okay, what I have is, and if I break this M12 moment resultant, okay, so the M12 moment resultant, this is y direction, okay, this is y direction. So M12 becomes a full moment when we multiply by d alpha 2. Okay, so that is a full moment. So if I say that I have this moment or this set of forces M12 over a distance delta alpha 2, okay, or d alpha 2, sorry, d alpha 2, d alpha 2, and I have the next set of moments M12 plus del M12 del alpha 2 d alpha 2 and corresponding, let me do it on the other page. So we have this direction is the alpha 2 direction, and then I have the moment M12 moment per unit length. So when multiplied by d alpha 2, it becomes a full moment. This can be taken as a force in that case. So what do I have? I have M12 and an M12 downwards, let's say. Okay, so this is d alpha 2. Then the M12 is changing, right? It's not constant. So I have M12, this is M12, this is M12. Then I have M12 plus del M12 by del alpha 2 d alpha 2. This is still a resultant into d alpha 2. Okay, that becomes a moment. So corresponding to this, I have the next downward force. So these two make a couple. These two make a couple. Okay, this is also d alpha 2. If we continue in this fashion, what happens is at every point I have an M12 downwards and an M12 plus an increment upwards, in keeping with the sign convention, okay, in keeping with the sign convention. So as a result, everywhere I have del M12 by del alpha 2 d alpha 2. Okay, this is a moment resultant, which is a force. Okay, then what do I have? I have Q13 into d alpha 2, that is a force. So this is a force, this is a moment resultant, moment per unit length, and this is hence that is a force. Okay. So I have this everywhere on that face, and I have this everywhere on that face. Both are forces now. Okay. And therefore this shear moment on this face has been made into an effective shear force, which is of the same nature as Q13 into d alpha 2. So that now what I have is, if I take d alpha 2 outside, I get Q13 plus del M12 by del alpha 2. Okay. So now if we bring in this combination, let us first see how the boundary condition looks like. It looks like T1 to T2 I will put the alpha M11 in the front, star M11, okay, delta beta 1, delta beta 1, okay, plus M12 star minus M12 into delta beta 2, okay. And here for delta beta 2 I will use the definition for beta 2. So I get beta 2 is equal to minus del U3 by del alpha 2. So delta beta 2 will become minus del alpha 2 delta U3. Okay. Then the final term, which is Q13 star minus Q13 delta U3 d alpha 2 dt. Now this is already at the ends of alpha 1 boundary, at the ends of alpha 1 boundary. Okay. So now what happens? Now what we have is that we look at this term here, we look at just this term over here. So we have an integral over an alpha 2 M12 star minus M12, okay, minus del alpha 2 delta U3 d alpha 2. Okay. So if we continue with this, I get a boundary term M12 star minus M12 delta U3. This is now at the ends of alpha 1 and alpha 2, hence it is a corner term. Plus integral alpha 2 del alpha 2 M12 star minus M12 delta U3 d alpha 2. Okay. So now if we combine this and this, because there is delta U3 here and delta U3 here, okay, by combining, what do we get? We get integral T1 to T2 integral alpha 2, and I get Q13 star plus del alpha 2 M12 star minus Q13 plus del by del alpha 2 M12 delta U3 d alpha 2 dt. Okay. So we will call this V13 star, we will call this V13, okay, the Kirchhoff effective shear stress term. And so if we now put this back into the original full boundary condition, I get integral T1 to T2 alpha 2 M11 star minus M11 delta beta 1 at the ends of alpha 1 plus V13 star minus V13 delta U3 at the ends of alpha 1 edge d alpha 2 dt. Okay. And another boundary or a corner term M12 star minus M12 delta U3 at the end of alpha 1 and alpha 2. It's a corner term. Okay. So that also gives a condition. Either U3 has to be specified or M12 is equal to M12 from the interior of the material at the corner. Okay. So we will be looking at simply supported plates, clamped plates, okay, which are fixed also at the corners, and therefore delta U3 will be 0. So this boundary term goes to 0. Okay. So similarly, for the alpha 2 constant edge, we get integral T1 to T2 integral alpha 1 M22 star minus M22 delta beta 2 alpha 2 constant edge plus V23 star minus V23 delta U3 at the alpha 2 constant edges d alpha 1 dt, and a corner term M21 star minus M21 delta U3 alpha 1 ends and alpha 2 ends corner. Okay. So that's the full story. The reason I am doing this repeatedly is that some of you may be familiar with just plates and some of you not familiar with Hamilton's law. Some of you have done it using force balance. So just to show you that for a familiar system how the same Hamilton's law works. So we have looked at a subset of the original terms because it's a flat structure. Okay. Now the last item along these lines before we move to the next topic is I would like to derive the same equation of motion for a rectangular plate using force balance, not Hamilton's law. Okay. So I will now use the familiar notation. U is the displacement in the x direction, v is the displacement in the y direction, and w the displacement in the z direction. Okay, so my plate looks like this. So this is my middle plane, that is x, that's my mid plane, that's y, and that is z. Okay. So then epsilon x x, so I am going to use the Euler-Bernoulli, or in this case the Kirchhoff set of assumptions. Okay, this is Kirchhoff plate theory. So epsilon xx is del u by del x, then epsilon yy is del v by del y, epsilon zz, as our assumption says, is del w by del z, which is 0. Okay. Then epsilon xy, okay, is del u by del y plus del v by del x. Okay. And epsilon xz is equal to del w by del x plus del u by del z, which is equal to 0 in our theory. Similarly, epsilon yz is equal to del w by del y plus del v by del z is equal to 0 also. The vertical shear strains are 0 for us. Okay, and we take the beta definition right away. U is equal to minus z del w by del x, which is beta 1, and v is equal to minus z del w by del y, which is beta 2. Okay, and along with this we have what? Sigma zz is also 0. So epsilon xz is 0, epsilon yz is 0, epsilon zz 0, and sigma zz is 0. Okay. So what happens to my epsilon xx? It becomes equal to minus z del 2 w by del x square, epsilon yy minus z del 2 w by del y square, and epsilon xy minus 2z del 2 w del x del y. Okay. Now we have to get to the stresses and stress resultants. So epsilon xx is 1 by E sigma xx minus mu sigma yy. Epsilon yy is 1 over E sigma yy minus mu sigma xx, and epsilon xy, the shear strain is sigma xy by g. Okay. As a result of this, we can find sigma xx in terms of epsilon xx and epsilon yy. So then sigma xx becomes equal to E 1 minus mu square epsilon xx plus mu epsilon yy, okay, and that is equal to E by 1 minus mu squared minus z del 2 w del x square minus mu z del 2 w by del y square. Sigma yy is equal to E by 1 minus mu squared into epsilon yy plus mu epsilon xx, and that is E over 1 minus mu squared minus z del 2 w by del y squared minus mu z del 2 w by del x squared, and sigma xy is equal to g epsilon xy, which is minus E z by 1 plus mu del 2 w by del x del y. Now we go for the moment resultants, okay, the moment resultants. Moment resultants. One thing I want to mention here is that everything is a function of z. Z comes in everywhere here, okay. So if I integrate this from minus h by 2 to h by 2, okay, which should give me the actual resultants, because there is a z, I will get a z square by 2, which over minus h by 2 to h by 2 will give me 0, okay. So all the other force resultants will be 0, nxx, nyy, nxy will all be 0. So only moment resultants survive. That is why I am just straight away going for the moment resultants. So what are the moment resultants? The mxx is minus h by 2 to h by 2 sigma xx into z dz dy, okay, this is a full moment. So this becomes equal to dy integral minus h by 2 to h by 2 sigma xx into z dz, okay. Now that is mxx into dy. So this is a full moment, this is a moment resultant. So all the moment resultants can be put together this way: mxx, myy, mxy is equal to integral minus h by 2 to h by 2 sigma xx, sigma yy, sigma xy, z dz, okay, and mxy is equal to myx, because the radii are infinite in both directions. Okay. And lastly, we will need the shear force resultants, which is the inconsistency in the theory. So we have shear stresses that are non-zero, or rather their integrals are non-zero, dz. Okay. So now if we substitute sigma xx in mxx, then what do we get? We get mxx is equal to minus a d del 2 w del x square plus mu del 2 w del y square myy is equal to minus a d del 2 w del y square plus mu del 2 w del x square, and lastly mxy is equal to myx is equal to minus d1 minus mu del 2 w del x del y. Okay. Now if we, here d is the bending stiffness, E h cube by 12 1 minus mu square. Okay. If we now look at the how the force resultants or moment resultants, force and moment resultants appear on the differential element. Okay. So it looks like time is running out, so I'll stop this lecture here and we'll look at that part in the next class and finish up with the derivation of the plate equation. Thank you.